Now that we've gone over arithmetic sequences, we can go over geometric sequences. As a refresher, for a geometric sequence, each term is found by multiplying the previous term by some constant that we can call r. So here's our rule for a geometric sequence. A sub n is equal to a sub 1 times r, that product, to the power of n minus 1. We need to determine whether or not these sequences are arithmetic or geometric. If they are either one of those, we're going to find the common ratio or difference. Ratio for geometric, difference for arithmetic. If it's not arithmetic or geometric, we're just going to put neither. For number 1, I'm going to check to see if it's arithmetic first, because that's usually easier for me to see. So I'm going to see what am I adding or subtracting each time. If that doesn't work, then I'll check geometric. So for number 1, to get from 8 to 12, we would add 4. But to get from 12 to 18, we would add 6. So this one's not arithmetic. Now let's check and see if it's geometric. To see if it's geometric, I need to figure out if there's something that I'm multiplying by every single time to get from one number to the next. So, to get from 8 to 12, I want to see if I'm multiplying, what I'm multiplying by to get from 8 to 12. So 8 times something should give me 12. When I divide by 8 and simplify, the thing that I would multiply here is 3 over 2. Let's keep checking that for every single value. To get from 12 to 18, let's see if 12 times 3 over 2 is 18. So 12 times 3 is 36, divided by 2 is 18. So far that 3 over 2 looks good. For 18 to 27, 18 times 3 over 2, 18 over 2 is 9, times 3 is 27. So here we're multiplying by 3 over 2 every single time. So our common ratio is 3 over 2, and this is geometric. In number 2, to get from 8 to 16, we could add 8. To get from 16 to 24, we could also add 8. And to get from 24 to 32, we could still add 8. So in this case, it is arithmetic. And our common difference, we're adding 8 each time. Find the nth term of each geometric sequence. So we know these are geometric sequences, and we're going to use the geometric sequence rule. So to find the 9th term, that means our value of n is 9. We don't know r yet, but we do know a sub 1 is 5. So now let's find r. How do we get from 5 to 10? We know this is geometric, so we know we need to multiply by something. So to get from 5 to 10, we would multiply by 2. To get from 10 to 20, times 2. 20 to 40, times 2. 40 to 80, times 2. So that means our value of r is 2. Now we can use our rule for geometric sequences to find the 9th term. A sub 9 equals the first term times r to the power of n minus 1. This becomes 5 times 2 to the power of 8. We're only raising this 2 to the power of 8. So let's see what 2 to the 8 is. That is 256. So we need 5 times 256, which is 1,280. That means the 9th term in this sequence, if we were to multiply by 2 over and over again to get to the 9th term, we'd get to 1,280. In number 4, we need the 15th term. Now we need to find out what our common ratio is. How are we getting from 0.01 to 0.001 to 0.01? Or how are we getting from the 2nd to the 3rd term, or the 3rd to the 4th term? Instead of getting lost in all of these decimals, since I know this is geometric, it doesn't matter which two I pick that are side by side. So I'm going to pick 0.1 and 1. So 0.1 times some r is going to equal to 1. So then r is 1 over 0.1, which is the same thing as 10. So my value of r here is 10. My value of n is 15 because I'm looking for the 15th term. And the very first term in my sequence is 0.001. So now we know everything for our formula, so we can figure out a sub 15. A sub 15 is 0.001 times 10 to the power of 15 minus 1, which is 14. So I need 10 to the power of 14, which is a very large number, times 0.001, which gives me 10 to the power of 11. Oof. 10 to the 11, which is going to have a whole bunch of zeros at the end. I'm just going to leave it in this format.